Okay, starting recording. Oh yeah, they use the same provider in the home. Okay, wait. Pause record. Okay, again, good morning again. So we started the session. So yeah, today's discussion is on finally on the analog to digital conversion. Yeah? So we will perhaps be continuing revisiting analog filter somewhere in the future. Um, but as we need to know that filtering as well as other signal processing can be done not only in analog domain, but can also be done in digital domain. So before we go deeper into the digital domain, signal processing as well as electronics, we need to do about how the signal, which is normally or naturally continuous, can be converted into something which is digital. Yeah. So what is actually the difference between analog signal and digital signal? So let me use this. So about analog digital conversion. So before a signal can be digitally processed, it needs to be converted or transformed into digital domain from the analog domain. So that's what the process that we call as analog to digital conversion or ADC. And similarly, actually, if we would like to use certain program, certain structure, certain control algorithm to control real life or natural process, usually we need first to convert the digital signal, our digital program, yeah, into analog domain signal. So that then it can use, for example, to control motor, to control lamp or light source, to control other motion or prime controller, and many other actuators. So the inverse of analog to digital conversion process is called as the digital to, so we call it like this, the inverse digital to analog conversion, DAC. So before we learn about the process here, analog to digital conversion and digital to analog conversion, what actually is analog signal and what is actually digital signal? How do the two differ from each other, and why do we prefer to have digital domain in this time compared to analog signal domain? So after the invention of computer, of course, then people use computer lots. The use of computer is increasing. First is maybe only for simple data processing, but later also computer has been increasingly used in instrumentation, also in biomedical instrumentation. The use of digital data enable the doctors or physicians, yeah, to store the data. So normally the storage has to be done in the analog form, for example, as printed form in the printing using ink and printer in a paper, yeah, which also is a data and can be used, but it is very difficult to reproduce the data, to send the data. For example, you have, for example, to use photocopier machine and then send it using courier, etc., or using postal service. But when it is stored in the digital format, then it is very easy to to transport the data, telecommunication means, yeah, now using a telephone line, using any other telecommunication means, satellites, and then now with the internet, it's easy to transport or to transfer the data, transfer the data to other places. The use of storage also would enable digital storage, enable person or the physicians to process the data after the data is taken. Previously, the data is in the just in analog form, yeah, as I mentioned, either recording on paper or in on the screen, and then it is very difficult to have the data being processed further. For example, if it contains artifacts, if it contains noises, etc., then not easy for the physician to process the data. He or she, the doctors, have to use his or her ingenuity as well as experience to interpret the data amidst the noise that come into the data from the measurement. So using digital, and when the data is converted into digital format, then we can use so many algorithms, and the algorithm can be changed also quite easily by reprogramming the system to process the data. Yeah, we can also do filtering, as we have learned for in the analog domain. Yeah, digital filtering, which low pass filtering, high pass filtering, we can amplify the signal easily just using multiply. Yeah, in programming, that the data is then being amplified. We can use averaging algorithm and many different types of averaging. We can produce secondary data from the original data that we obtain. Then this is not easily done in analog domain. So in analog domain, as we have learned so far, the signal is continuous. So we have here, for example, signal, arbitrary signal. Yeah, for example, this is any signal, can be voltage, can be ECG, from ECG, EEG, etc. Yeah. This is just an arbitrary signal as a function of t. Yeah, t here is time in second, for example, in second or millisecond can also be millisecond. So yeah, now I erase everything. Okay, let's say for for example, this is an ECG signal. We have here P, Q, R, S, T, for example. Okay, so the signal, the original signal in biomedical signal is continuous. Yeah, so they are continuous. What does it mean with being continuous here? This is analog signal. Is the data has continuous value, so it's not discontinued. It's not cut, but it has a value at every point of time. Number one, it has continuous value in time. So you see here, when time proceeds, then the data is not interrupted in any way. So it is there. The analog electronics capture everything. Yeah. So of course, this is the good part, yeah, in analog domain, but also not good. It can be good, but it's also not good in one way. So then it is also continuous in values. Continuous value. It has continuous values in the signal itself, in the parameter itself, You see here that in the y-axis, in the analog system itself, for example, in the case of ECG, it will be voltage. Yeah, it doesn't have any discretization. It doesn't have any what we call as quantization. It is continuous. All values in the real domain, in the real number domain is there. Okay, and well, of course, within the limit of the instrument itself, in the limit of the amplifier, the limit of the analog filter itself. So this is the important two characteristics: continuous value in time and continuous value in the parameter itself. So when then we convert this into digital domain, what will happen is both will be discretized and quantized. Discretized will be discontinued. Only we use different terminology. Discretization in the time domain and quantization in the parameter domain. Okay, first is what we call as discretization. Discretization. So in discrete, discrete signal, we call it, so it becomes discrete signal, but not yet a digital signal. What we call as discrete signal is when the signal is being sampled and then hold. So this is called as true sample and holding. through the process called as SNH, sampling and hold. Sampling and holding. Holding means that the value is being stored. Okay, sampling and holding. Sampling means that uh, the previously continuous signal in time will be sampled every period of sampling time. Every period of sampling time. So depending on the on the speed of that ADC. So we can sample, for example, every a thousandth of a second. So every 1 millisecond. So it means then every 1 millisecond, the continuous signal is being captured or sampled. It's called the sample, and then hold. Hold then means being stored somewhere in the memory or in the register, something like that. Yeah, in the digital electronics. So then capture the next one, etc. So if previously this y equals to xt, right? This is a continuous signal, which we learned multiple times from high school, even elementary school, high school, and then also university. But then when it is being sampled, it is not continuous anymore in the time domain, but still continuous in the parameter itself. So we have, if, for example, from here, sampled means, let's say every the period is t, the sampling period is t, so every n t it is sampled, yeah, where n equals to 0, 1, 2, etc. 0 is 0 second. So here it is sampled here, there, for example, here. With the periodic sampling period, yeah, something like that. So what is being captured is the value of that signal at that particular sampling period. So the line is here, the red line, just to show where the sampling happens in the particular time. So if we redraw it in the discretized signal as a discretized signal, what it will look is, yeah, maybe something like this. Yes, it's not perfect, just to show you the how discretization happens. Yeah, so sorry, yeah, so my redrawing is not perfect, but the point is, what I would like to convey here is the signal is now discontinued in the time domain, but the value in the parameter itself is still continuous. So it could take, the value here could take any value in the y-axis, in the real domain. Okay, in the real domain, it could take any value. Of course, then the value between the sampling will be lost. Okay, the value between the sampling will be lost. So later I will show. So let me redraw first. Yeah, sorry, it takes some time. Okay, anyway, I hope you get that point. So this is sampled in, let's see, it's using line here. Yeah, better using drawing. Yeah, so every point here is sampled at that particular time. Yeah, so what about the value? Ah, so what about the value in between them? The value between them will be lost. Okay, so uh, during the discretization, time, some value will be lost, especially the value between the two discretized value. Okay, discretized period. So here is, look here, the period of sampling here, for example, if we This is the sampling period. Yeah, T here is sampling, we call it sampling period. The time it takes between each sampling or between each discretization. The inverse of T is called as sampling frequency. Yeah, so Fs, the sampling frequency, is basically the inverse of T. So Fs here equal to sampling frequency. So it means what does it entails? What does it entail? It means if we would like not to have many data loss during the discretization, what we need to do is we have to have a very high sampling frequency. Okay, so it means if we have very high sampling frequency, the period of sampling or sampling period is small, right? Because it is inverse. If Fs is high, it means T is very small. Okay? If T is very small, the sampling period is very small, it captures very quickly. It samples very quickly. So this distance between each point becomes very close to each other, which then resembles the analog signal more. It will be more closer. The discretized signal will resembles the analog signal better. Compare if you have a very small sampling frequency. So if you have small sampling frequency, then what it will happen is that your sampling period is wide. If your sampling period is wide, then you lost more analog data between the sampling. So understood, yeah? Everyone understand until here? So this is later, we will come back later in the slide when we explain the details of this. So an important parameter when we choose analog to digital converter, yeah, for example, we do not design ourselves the analog digital conversion, but instead we just pick off the shelf analog digital converter. One important parameter is the sampling frequency. So it is usually either can be expressed as hertz, yeah, similar like normal frequency, but people usually in analog digital conversion use a more specific term called as sampling per second, SPS, sampling per second. So if we have, for example, 1 kSPS, so it means we sample how many times per unit time? 1,000 times, yeah, per second, 1,000 times per second. The oscillator must generate frequency higher than 1,000 hertz because it needs to sample every 1,000 every 1 millisecond, 1,000 times per second. If we have, for example, 1 mega sampling per second, so if we have 1 MSPS, this is 1 mega sampling per second. 1 mega, 1 million sampling per second. Even some analog digital conversion can do 1 GSPS, 1 giga sampling per second, 10 to the power of 9 sampling per second. Of course, then it means how many? Every 1 nanosecond, it sample the data, the analog data, analog continuous data. Of course, then the reconstructed digital data will resemble more the real analog signal. Okay, so this is the disadvantage of one of the disadvantages. Later, we come to the second stage. After discretization, what will happen? One of the disadvantage of digital data is it does this discretization to the analog signal. So as a result, then the continuous value in time is lost. The continuous value in time is lost. You don't have any more continuous value in time. Some values in the real analog data is gone, which are the values between the sampling. How to reduce this? Of course, then you increase the sampling frequency or reduce the sampling period so that sampling happens more every unit time. However, this comes with a cost, of course. More energy will be required. Okay, more energy will be required. Okay, so um, we have mentioned the advantage of digital data, yeah, that it can be stored easily, it can be transmitted easily, it can be processed easy. However, the disadvantage is then the data does not resemble, or the data is not, we call it, is not the original analog continuous data, because some of data have been lost during the discretization process. If we don't want that loss to be too much, then what we can do is the sampling period has to be lessened, or inversely, the sampling frequency has to be increased. So then, instead of having y equal xt like this, the continuous data, what we will have is, will be y equal to x and t. Okay, so where uh, yeah, so then plus x n plus 1t, yeah, plus x n, sorry, n not n plus 1t, yeah, n plus 1t, n plus 2t, etc. Yeah. So where, or not n and 1t, yeah, but 2 and just nt like that, yeah, plus 2 nt, etc. So this yeah, 2 nt and then 3 nt, etc. So the data is now not the, this is until infinity, okay? So not the continuous data like before xt and t, yeah, but instead it is the data of the original one, but which is only at particular points, which is the multiplication, integer multiplication. So n here equal to 0, 1, 2, etc. Integer multiplication of the sampling period. Okay, until here, clear, yeah? So this is what we call as discretization. So I save this, discretization. But the process is not finished the time. So I will clear first here, continue. After being discretization, then we have another process called as the quantization. Okay, called as quantization. So what does it mean with quantization? If previously the discretized data obtained, so let's just redraw the discretized data. This one, okay. So from the previous data, we obtain discretized data, yeah, from n equal to 0 second until, for example, it is 1000 millisecond, the sampling period, then t equals to 1 millisecond, right, this, then 2 millisecond, 3, etc., etc., yeah, until so and so forth. Even though they are discretized in the time domain, but they can still have any value in the y-axis. It can still have any value in the parameter, in the original parameter. For example, if in the case of ECG, that will be voltage in millivolt region or volt region, depending on whether it has been amplified or not, and any other data. So we call it this discretized data. Okay, just draw for the sake of, so we know where it is being discretized. Then with the second process in quantization, yeah, the signal value is quantized to, is being quantized to the closest step value, the closest step value, step or staircase value, the closest step or staircase value. What is that? What does it mean with staircase value? So, for example, we from this whole value of x, or also this is time in second. So, for example, this is x value. Then it will be quantized further. It cannot have any value in the y-axis, but instead it will be rounded, yeah, rounded to the closest step. So this continuous value, for example, every this value of let's say a, yeah. So then we see that if like this, for example, this one, it will be rounded to this value, to the value below it, yeah, and maybe some value, this one will be rounded. So for example, this value below it. Yes, this staircase value is above it, so this value will be rounded to above it, yeah, because if that value is above the zero, the half of the difference, yeah, this a, it is the difference between the two step, yeah, then it will be rounded to above. If it is below that 0.5, rounded below to the lower value of the staircase. Let's say we call it staircase values. But if it is above the 0.5 value of the difference, it will be rounded to the upper value. So this is called as the quantization. So what we will have later, yeah, we will lose then. In the previous discretization, we already lost the value between two sampling periods. In the quantization step, we will lose further the value of the signal between the staircases value. Okay, so this is not the loss in the time domain, but instead the loss of values in the magnitude of the signal itself. So instead of continuous value like this, we will have, usually it is, we will have a step value like this. So this is step, the original, uh, something like this. Middle is the to represent the value. So it is being, so now it is all being considered constant in this t, or throughout this t sampling period, yeah, which with a value approximated from the previous discretized value. Approximated here means that the discretized value is being rounded to the closest staircase value. Okay, this, so, yeah, something like this. That is just approximation, yeah, not to be taken to be exact as the previous picture above, yeah, but instead just to show you the point that now it is being discretized to this value depending on these levels of the stairs. Okay, so now what if we want that the value being lost is not that many? So we don't want too many losses. So what we can do is that the staircases, the difference between each staircase should be as small as possible, right? If the steps is too high, it means then the rounding becomes too big. We'll make a too big difference with the original value. And let's say, for example, let's say just an example, we have the A here, yeah, the A here, let's say 1 volt. The difference is 1 volt. Let's say we have a value of 0.6, then it will be rounded to 1 volt. If we have value of 0.3, it will be rounded to 0 volt, right? But if we have, for example, A, so here you see the difference is 0.4 volt, positive 0.4 volt from the original value. Here the difference is 0.3 volt from the original value. But let's say now A is made smaller to be just 0.5 volt. We make it even smaller, yeah, only 0.5 volt. So what will happen is The 0.6, if it is 0.6, it will be rounded to 0.5 volt. 0.3 will be rounded to 0.5 volt as well. So here the difference will be 0.1 volt. Here the difference will be 0.2 volt. Although they now become the same level, but the difference to the original value becomes smaller compared to the if we have A is 1 volt. So if we want the data, the digital data to approximate the original analog data more closely or closelier, then we have to make A as small as possible. What does it mean, as small as possible? The quantization, the n, quantization, the small n here, should be as large as possible. And here then represent a bit. Why this quantization happens? Yeah, because now instead of continuous data, continuous real data from zero, let's say zero could be 0.1, 0.2, for example, until as well as the values in between. Now we only can represent it in digital data. Digital data is in binary, so in 0 on or 1. 0 and 1, then it means depending on how many bits we have, yeah, let's say if we have 2 bits, then we can represent 0, 0, 0, 1, 1, 0, 1, 1. If we have 3 bits, we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, then 1, 1, 0, then 1, 1, 1. So 8 levels of data. Then this is then depending on the voltage, the reference voltage. So if we have, for example, reference voltage of 10 volt, same. So if we have only 2 bits of resolution, we call it, then so we have here resolution in the quantization. Yeah. If we have 2 bits, then this 10 volt will be divided into 10 volt divided to 2 power n, to the power of, so if it is 2, n equals 2, yeah, the bit, the 10 volt divided by 4. So what is the level? 2.5 volt. The A will be 2.5 volt. The A, this becomes the A. The difference, yeah, or the you can call it resolution. But if instead, if n is 3 bit, then A become 10 volt divided by 10 to the power of 3, 8, right? So 8, so means 1.25 volt. The level, the A will be to 1.25 volts. Okay. So the resolution which we obtain depends on the reference voltage here, as well as depend on the n. And the n is how many binary digit representation that we use to represent the analog signal into digital signal. The more n we have, as well as the if we have the more n, it means then we have the smaller a. Yeah. Similarly, if the reference voltage is not too big, yeah, the reference voltage is not too big, we have also smaller a. Okay, so we usually 10 volt can be used, 5 volt is can be used, later also 3.3 volt can be used as a reference voltage. Then but usually that is taken as standard, either 5 volt TTL level or 3.3 volt. Now the new TTL level is 3.3 volt. So what we can usually choose is the n here, the resolution bit. The resolution bit. How many n you choose? Is it 2-bit, 3-bit, 4-bit? Yeah. No, usually no ADC has 2-bit resolution now. At least they have 8 bits. Yeah, 8-bit data. 8-bit means n equals to n. If n equals to n, then 2 power 8 is about 256 level. This is the smallest now they have in the market. Yeah, even they have now much higher resolution with n equals to 12-bit resolution, 14-bit resolution, 16-bit resolution, 20-bit resolution, and some even have 24-bit resolution. So depending on your application, if you want higher accuracy, so your digital data represents the analog data closer, then you should choose a higher end. Okay, higher end. However, of course, this comes with a cost again, similar like the discretization process. Yeah, in the discretization process, you will, if you want uh, uh, your data to be representing the analog signal more, you desample more. Desample more means require more energy. Similarly, if you want your data to be accurately represent the analog data, you want the quantization to be as small as possible. So the A become as small as possible means you have to increase the N, the bit resolution. So what happens then may also cost some time. Yeah, because in order to chop into and to quantize into more bits, you need more time. So later when we study on types of the analog digital converter, for example with flash and ADC, then the it is very fast, but the quantization becomes not that accurate. With a more accurate ADC, sigma delta or other algorithm, it is not that fast. But of course now with the advancement of electronics, the electronics can be compacted, can be made very small and smaller, then this is it can be compromised. So you can still have relatively fast sampling, but with relatively accurate quantization. Okay, so we will study more of this in the next session. So now we'll stop